Hello, and welcome to another tutorial about working with a simulation workbench. This video will review the workflow used in creating every simulation project. Every simulation project requires creating solids and defining the appropriate links between them before running the simulation as a first step. I'm going to open a model in SimLab Composer. This model requires 3 revolute joints and only 1 prismatic joint to work properly. In order to do that, let's switch to the simulation workbench. Keep in mind that the first step in every simulation project is to define and create solids from the original geometry of the model. Using the Solids tab, you can create solids using either the Detect button or the Manual Solid Creation button. Here we can take advantage of the Detect button's help for automatic detection of the solids. The model's geometry has been defined and classified into solids as shown in the solids tree, causing the model's geometry to disappear from the geometry tree. The newly created solids are slider, rotor, track, and link. You'll notice that the links tree is still empty. Now try to run the simulation to demonstrate the behavior of the current model before applying the joints. The next step is defining relationships between 2 solids. Using the Links tab, you will add the joints to control the mechanism behavior. The first joint will be a revolute joint between the motor and the ground with enabled motor. Click the Revolute button from the Joints toolbar. The Link Properties panel appears. Rename the joint. Pick the rotor solid for the first solid. Pick the ground for the second solid. In order to specify point and axis of revolution accurately, click the Pick button, then from the Common toolbar, select the Pick Center of Curvature tool. Click Enable Motor. Select the Torque Radio button for the motor control mode, then click the Edit button. The Function Editor dialog box appears. Enter 1 as the new value for the constant motion function and press OK. Try to run the simulation again to demonstrate the new behavior after applying the rotor joint. Stop the simulation. Now to the second joint. It will be a revolute joint that connects the rotor solid and the link solid together. Click the Revolute button from the Joints toolbar. The Link Properties panel appears. Rename the joint. Pick the rotor solid for the first solid. Pick the link solid for the second solid. Before specifying point and axis of revolution, we need to hide the link solid to allow us to see behind it. Return to the Link Properties panel after selecting the new link. In order to specify the point and axis of revolution accurately, click the Pick button. Then, from the Common toolbar, select the Pick Center of Curvature tool. Now show the link solid. Rerun the simulation to demonstrate the new behavior. Stop the simulation. For the third joint, click the Revolute button from the Joints toolbar. The Link Properties panel appears. This joint will connect the link solid with the slider solid. Rename the joint. Pick the link solid for the first solid. Pick the slider solid for the second solid. In order to specify the point and axis of revolution accurately, click the Pick button. Then, from the common toolbar, select the Pick Center of Curvature tool. Rerun the simulation to demonstrate the new behavior. Stop the simulation. And now for the last joint. The fourth joint will be a prismatic joint between the slider solid and the lock track solid to implement the linear sliding movement between them. The two joint solids will have their rotation held fixed relative to each other. Before adding the prismatic joint, we need to lock the track solid using its properties panel in order to make it fixed in space, invulnerable to any external force. Select the track solid. Its properties panel appears. Toggle the lock button. After locking the track solid, click the prismatic button from the Joints toolbar. Rename the joint. Pick the slider solid for the first solid. Pick the track solid for the second solid. In order to specify the point and axis of sliding accurately, click the Pick button. Then from the common toolbar, select the Pick Edge Loop tool. Choose the green face. Rerun the simulation to demonstrate the new behavior. Stop the simulation. Sometimes you may need to change the simulation parameters before attempting to run the simulation, or after stopping the simulation in order to configure the settings to your requirements. This can be done by the Parameters button. Click the Parameters button. The Simulation Parameter dialog box appears. It allows you to set up options related to the chosen solver and other general and advanced options. Finally, for the purpose of simulation data analysis and post-processing, use the plotting library to represent the simulation data set visually as graphs. It allows you to show the relationship between two or more variables. The plotting area allows you to draw up to 4 graphs simultaneously. For this tutorial, let's set up 2 graphs quickly. Activate the first plotting area by selecting it in order to add curve channels. Click the Manage Curves button. The Manage Curves dialog box appears. To draw a new channel in this selected plot, enable the selection tool by clicking the plus button to select the desired entity, either from the 3D area or the corresponding tree. After selecting an entity, all the corresponding channels appear in the Manage Curves dialog box. Select channels to be plotted in the active plot. Then click OK. Perform the same steps for the second plotting area. Run the simulation to watch the second plotting area being updated in real time. This is a quick tour for introducing the simulation workflow. Thank you for taking the time to watch this video.